The next function example is similar to the Dirichlet function in that it is a piecewise function. It's defined in one way if x is a rational, and another way if x is irrational. So in this case, instead of having a 1 here, we put x squared. So let's take a look at what the graph looks like, and that sometimes helps us answer this question just by looking at the graph. Okay, here's the graph of f of x equals x squared. I'm going to do it with dots. Since it's only f of x equals x squared when x is a rational number. And then I guess for the x-axis, I'm not going to draw it solid, I'm going to draw it like this. Similar to the way we did it before. So for example, f of 0 is 0, f of 1 is 1, f of 2 is 4. When you get to the irrational numbers, like f of radical 2 would be a 0, f of pi would be a 0, and so on. So perhaps looking at this picture makes it a little bit easier. All of the dotted lines on both this and this are the function. Does it look like the limit might exist anywhere? Good. Yeah, the limit exists at 0, and we're going to show that. I'll put x naught equals 0, and it's only there. Only at x0 equals 0, and we're going to use the delta epsilon definition of a limit to prove that. So, in order to do that, we're going to show or prove that the limit as x approaches 0 of f of x, I assume you were going to say that the limit is 0 as well, right? The limit exists at x equals 0, and the limit itself is 0. So when I'm going to do a proof like this, I have to use the definition. So what's the very first thing I write? Say again? Oh, that's the definition. The definition. That's good. For the proof, all I need to say is let epsilon greater than 0 be given. So just let epsilon be greater than 0. Since it'll work for any epsilon, we're showing that it's true for all epsilons. All right, well, I'm going to take a stab here and say, choose delta equal to epsilon. Now, I might come back and change that by the time I get to the end of the proof, okay? Let's just see what happens when I say choose epsilon equal to delta. I need to find an epsilon such that the definition of a limit holds true. And let's see what happens here. So, let x be such that, I'll go ahead and say x a real number. That's only because x is the real number. The domain of this function is all real numbers. So let x be a real number, and let it be such that it's close to x naught. Let's say that that's less than delta. And then I'll just make a note. We're going to do that to prove that f of x minus the limit, which is 0, is less than epsilon. So this was an optional thing to write, what I'm underlining there. That's just telling the reader of this proof where we're going. So let x be close to x naught within delta, and we're going to have to prove that f of x minus the limit, which is we're showing is 0, that's, in other words, f of x is within epsilon of 0. So that's equivalent to this. I didn't need to put the minus 0, but since 0 is the limit, I went ahead and put that in. All right. Here's what I need to show. So f of x minus 0, which I'm going to just start off by saying is f of x in absolute values. Now then, true or false that that is less than or equal to x squared? Is f of x less than or equal to x squared? Well, f of x is either x, well, actually, I don't need the absolute values around the x squared because x squared is always non-negative, but it's okay to have it. And were you going to say something, Numby?
No, I was just saying that's true.
It is true. Because f of x is either x squared or it's 0, right? So f of x is always less than or equal to x squared, okay? Now, the next statement, is this true? I can put here by definition of the function, absolute value of f of x is less than or equal to x squared because it's either equal or it's 0, which is less than or equal to x squared. Can I do this though? Can I say that, can I make that next statement? Look at the graph. Is the graph of x squared below the graph of f of x equals x? Let me use a different color here. Let's see here. The graph of the absolute value of x looks like this. So true or false? X squared is less than or equal to the absolute value of x?
Not always.
Not always. Where is it true? Between -1 and 1, right? If that's -1 and that's 1, x squared is less than x. For example, 1/2 squared is less than 1/2. Because 1/2 squared is 1/4. They would be down below the graph. But once you get to 1, where they're equal to each other, because 1 squared is 1, once you get beyond 1 or to the left of -1, x squared starts getting a lot bigger. So what can I do to make that statement? It's true if x is between -1 and 1. So all I'm going to do is force delta to also be smaller than 1. So what I'm going to say is let delta be the minimum of epsilon and 1. So even if we chose an epsilon to be really big, my delta I'm going to choose to be less than 1. And now this is true. Let's make it clear. I'll put since x is in between -1 and 1. It's in the interval of -1 and 1. Well, we already know that right here, we know that that's less than delta, which is less than or equal to epsilon. Is that right? Because delta could equal epsilon. So delta could be smaller. I should put that the other way around. That's less than epsilon, which is less than or that's all I need. That's the end of the proof.
Because it's strictly less than delta, then it's strictly less than epsilon.
That's correct. It's not strictly less, but I mean delta could be equal to epsilon.
No, I mean like the x.
Oh yes, exactly right. Yes. Because remember that And you could actually change this in the proof if you wanted to. This minus x naught, well, x naught is 0. So if you want, you could just put the 0 right in there, which means that's less than delta. And epsilon is either equal to delta or less than delta. Right? Did I say that the right way? This is either equal to delta or less than delta. This is either equal to epsilon or less than epsilon. Did I say that right? Yeah, if delta is big, then this would be equal to a 1. So that's the proof. This graph helped us out. Now, another way to think about this, though, is I like to look at the graph and say, what are the, if you're a sequence that's converging to 0, if you're on the x-axis, how can you get there? How can, if you're at the sequence xn, f of xn, as if xn is approaching 0, f of xn is either traveling along this, and as you get to 0, the height of the function gets to 0, or it's traveling along this, where it's the constant 0, or it's a combination thereof. It goes from here to here to here to here to here, but notice what's happening. It still hones in on the height of 0.